We'll go quickly over the solar system debris. The first type of object that belongs to this category are asteroids. And the largest one is asteroid Ceres, which has a diameter of about 1,000 kilometers. And it was discovered at the beginning of the 19th century by Piazzi. There is a story behind this. There is a piece of numerology contained in so-called Titius-Bode law, which gives a rule as to how you can find the distance of a planet from the sun. So you start first with 1, you add to that 3, and divide by 10. So 1 plus 3 is 4 divided by 10 is 0.4. That is approximately the distance of Mercury from the sun. Then you add 3 to 4, the previous number, which is 7, divided by 10. You get 0.7, which gives the distance of Jupiter from the sun. You add 3 to 7, divided by 10, you get 1. That's the Earth's distance, and so on. So a lot of planets were fitting that rule. As far as we know, there is no basis for it. It just happens to be an interesting piece of numerology. But it motivated Piazzi to actually look for a planet, for the 9th planet, because at that time people didn't know anything about Pluto. And in fact, there were less, Uranus and Neptune. So he was looking for an extra planet just at about the right distance, and he found Ceres, which is, as we now know, an asteroid, but it happens to be the largest asteroid. It is located, and most asteroids are located in so-called Asteroid Belt, which we mentioned at the beginning of our discussion of the solar system. It's a region from about 2.2 to about 3.3 astronomical units from the sun. So this is the diagram that I've shown before. Here is the sun, our Earth, Mars. Here's the orbit of planet Jupiter. So the asteroid belt is roughly halfway between the orbits of Mars and Jupiter. And this line here tells you what kind of objects, how they typically look like. In addition to the asteroids in the asteroid belt, we also have these so-called Trojan asteroids along the orbit of Jupiter. They are 60 degrees ahead and 60 degrees behind Jupiter. And there are also, the third major group are Apollo asteroids, which have highly elliptical orbits that cross the Earth's orbit, right? So they are so-called near-Earth asteroids. All of them have a prograde or counterclockwise motion. And we can understand why if we recall the likely scenario for the formation of the solar system, where there was that collapsing cloud that was spinning, and as it was collapsing, it flattened out, but the angular momentum conservation actually ensured that the angular momentum is the same, therefore they all orbit in the same direction. And it turns out also that their orbital planes are very close to the orbital plane of the Earth, so-called ecliptic. Moreover, the asteroids in the belt have nearly circular orbits, while Apollo asteroids have highly elliptical orbits which intersect the Earth's orbit. Now, they range in size tremendously from the largest one, Ceres, to about 100 meters across, and there are estimated 25 million of these smaller asteroids. The large ones, like Ceres, they have spherical shape because their mass is large enough so that they assume spherical shape under the influence of their own gravity. But the smaller ones, like asteroid Gaspra, they have irregular shape. Right? It's shaped like almost like a potato. You can see these impact craters, and the dimensions are, the longest dimension is about 18 kilometers, and then the two cross dimensions about the same, 9 kilometers. Okay? But it's still fairly large body, right? However, it's small compared to the largest ones. It turns out that about 1/3 of all of the mass of all the asteroids is contained in the largest one, in the asteroid Ceres. Okay, so most of the mass of the asteroids is in the large ones. But it turns out that the total mass is quite small. If you would put them all together, you would produce an object that is barely 1,500 kilometers in diameter, and with a mass that is only 0.04% of the Earth's mass. And it is estimated that the average spacing between the asteroids in the belt is about 1 million kilometers. Okay, so it's not that they are very close to each other. The average spacing is on the order of 1 million kilometers. So the question is, how come that this material didn't come together and form a planet? And the answer is similar to the answer to the question why there is a Cassini's division in the ring structure of Saturn. It turns out that a nearby large, very massive planet, the largest planet in the solar system, that is about 320 times more massive than our Earth, exerts tremendous gravitational influence in that region, so it did not allow a single object to get formed. Also, Jupiter is responsible for the gap structure in the asteroid belt. There are gaps where there are no objects, and the explanation is pretty much the same as the explanation for the Cassini's division in the rings of Saturn. Basically, you get gaps where you have a so-called orbital resonance with Jupiter. So for instance, there will be one gap corresponding to the objects moving along the orbit whose orbital period is a half of the orbital period of Jupiter. Then you can also get a gap where the ratio of the orbital period of Jupiter to the orbital period of would-be object in a gap is 3 to 7, and so on. So it is the resonant gravitational pull by Jupiter that is causing these gaps in asteroid belt. Okay, so let's look at what they are made of and how we classify them. There are three basic groups of asteroids: C asteroids, S asteroids, and M asteroids. And C asteroids form the majority, about 3/4 of all asteroids, 75% are in this group of C asteroids. And they have a very low albedo. The albedo is between 3 and 4%, so they look like a lump of coal. They reflect very little sunlight. And when you analyze their chemical composition, it turns out that they are composed of silicate material mixed in with the dark carbon compounds, and hence the name C asteroids for carbon. And it is these carbon compounds that give them this low reflectivity. And it turns out that most of them are located at the outer edge of the asteroid belt, closer to the orbit of Jupiter. S asteroids form the second largest group. They constitute about 17% of all asteroids. And an example of S asteroid is Gaspe, that I just showed a few pages before. They are brighter than C asteroids with albedo of between 10 and 22%. And they have appearance of a stone because their surface certainly consists of silicate materials, right? And for that reason, they are called S asteroids. With these asteroids, there are no carbon compounds leading to a low albedo of the surface. And they happen to be, most of them happen to be located near the inner edge of the belt, closer to the orbit of Mars. And the last group are so-called M asteroids. They are the smallest group, and here are photos of asteroids that belong to this group. They have medium albedo. Some of them, but not all, are made of metals, nickel and iron, right? And hence the name M asteroids. And they happen to be located in the middle of the asteroid belt.